In the last video, we saw that harmonic series 1 plus a half plus a third and so on does not converge. However, the interesting thing is the alternating harmonic series 1 minus a half plus a third minus a quarter, this does converge. And in general, this alternating series where I have the signs changing from plus to minus and so on, this behaves much better than the usual series, behaves better than this usual series that we saw in the last video. I'll leave a link to the video. And also one more thing, not only is it better behaved, it has beautiful properties, really beautiful properties, and this is the reason why they make you study alternating series in college. It's a very beautiful topic. And we will need it because we need this for some proofs and some videos that I will be doing coming up soon. Let's look at the alternating harmonic series more closely. You will notice that the even terms are negative. So that's the general rule for any harmonic, for any alternating series, not just the harmonic alternating series. We can write this like this. Sigma k is 1 to infinity minus 1 k plus 1, because we want the odds to be positive. So when k is odd, this is even power, and this becomes plus 1, and then 1 over k. So in general, an alternating series looks like this, and it's the same phenomenon. Okay, the odd terms are positive, the even terms have a minus in front of them, and I can write this as k is 1 to infinity minus 1 k plus 1 a k. So I'm doing this to factor out the minus 1. I want my ak's to be all positive and consider the negative elsewhere. So just keep in mind negative, negative, and so on and so on. It's always like this with alternating series. Great. Now let's plot our harmonic alternating series. To do so, we have to introduce, like before, the partial sums. Like this. This is partial sum S1, S2, S3, S4. Notice that when the partial sum is even, I'm always subtracting something from the end of it. So it kind of gives you some intuitive feeling right away that maybe it's going to be smaller. And we can write partial sums like this. Sn is sigma k equals 1 to n minus 1 k plus 1 power k plus 1 ak, and in this case it's 1 over k. And in general, my partial sums for any of these alternating series will be a1 minus a2, a1 minus a2 plus a3, and so on, a1 minus a2 plus a3 minus a4, and there's my expression for general partial sum for any alternating series. It will look like that. All right, so I want to plot this. I want to have a look at how my harmonic alternating sum behaves. So I'm going to plot these here. Let me use color for that. I'm going to plot these here partial sums. Let's see, do I have enough room here? Yeah, maybe. Kind of, yeah, not really. Well, okay, that sort of fits. Well, so I have this number 0.6931, and it seems my partial sums S1, S2, S3, S4, and I follow the jagged line, and those are my partial sums, the red dots. They seem to be converging to this number. Some are below, some are above. If anybody knows what this number is, why don't you write it in a comment? What is this 0.6931, which looks like it should be the limit of this alternating sum? So this is my harmonic alternating sum, and I've got these partial sums up and down here. So what I'm going to do is naturally divide my partial sums into two types. And you'll see why in a minute, because you'll see here that there's the type which is above 0.6931 and the type which is below. So here's the natural separation into two classes. I have the odd partial sums, which is sum of an odd number of terms. I can look up here and see, all right, this is one term. This is three terms. These are all odd partial sums. And I write it like this, 2n minus 1, because when n is 1, 2, 3, and so on, these are always odd. And now I have another class of partial sums, the ones that have an even number of terms. Again, when n is 1, 2, 3, this is always even. So I sum an even number of terms. Going up here, we see, let's use a different color. This is even, 2 terms, 4 terms, that's even, even, you see? So you'll see in a minute their behavior is totally different, but very, very beautiful. So let's plot that behavior here. Here are my even partial sums. They just so happen to be the ones at the bottom. So this is S2, S4, S6, and so on and so on. And notice that they seem to tend to the limit from below. So we can write it like this. S2n approaches the limit from below. They start off small, but they get bigger and bigger and approach the limit. And now the odd partial sums, they are the blue dots above. That's very beautiful. S1, S3, S5, they seem to approach the limit from above. Well, this is truly beautiful behavior. It turns out that our choice of separating the partial sums into two classes, this type and this type, was a good idea because it naturally separates out what's going on here. And this is the first example of something very beautiful about alternating series. You have to admit this is really cool and really beautiful. And now I want to point out that this is not just the case for AK is 1 over K, which is what I've been plotting here, but this is the case for all reasonable alternating series. They're much better behaved. It doesn't take very many conditions to have them behave this way, and we're going to prove all of this in the next sections. So here is an outline of what we will prove about alternating series. Let AK be a sequence, and this sequence has 3 properties. First of all the AK are positive. Secondly, the sequence AK, K is 1 to infinity. This is monotone decreasing. Monotone decreasing. And finally, so this is property 1. I can put a box. Property 2 is this one. And finally, the third property is the limit as k goes to infinity of AK is 0. So these are very simple properties, and for typical series, yeah, it's true. For harmonic series, it's true, but harmonic series doesn't converge. This is true for harmonic, this is true, but it still doesn't converge. But for alternating series, yes, it does converge, and we have some other beautiful properties. So if this is the case, then I have 1. The series, the alternating series, k equals 1 to infinity minus 1, k plus 1, ak has a sum. And what does that mean? It means that the limit of the partial sums exists, and we can call this S. Okay? So that's what it means in a rigorous sense when a series has a sum. So we have that. This is automatically, we get that from this with no further thought, unlike the case with regular, normal, usual series. But we have more. We have also that the truncation error is easy to estimate. What do I mean by this? Well, suppose I'm estimate the limit, the sum of the whole thing by let's say the nth partial sum. So what happens if I go up to n and then I truncate the series there? How far off am I wrong? So I have a1 minus a2 plus, so this is my partial sum. Well, let's write the whole thing out. So I go all the way to Sn. Now, I don't know if Sn is odd or even. So the nth term, well, let's say it's plus or minus an. I don't know if it's odd or even. But if it's plus, then the next one is minus. So I'm going to have something like this, an plus 1. And then this is going to change n plus 2, and so on and so on. And this goes on to infinity forever. And this whole thing here, let me use some color. This whole thing here, this is my sum s. This is the limit. This is this s. But this here is my estimate. So I want to know, how big is my estimate, or how far off is my estimate? Well, it turns out I have this beautiful thing, s minus my estimate, absolute value of this, is going to be, it's going to be less than or equal to the next term, the magnitude of the next term. So this is less than or equal to, let's get black back, less than or equal to an plus 1. This it's hard to read. That should be a plus 1. So that's beautiful because it's very easy to understand this error estimate. And in fact, this is the thing that we really, really want, because I want to show you in an upcoming video very soon a spectacular theorem that needs this. That's why I want to talk about alternating series. That's one reason. There's a spectacular theorem, and this is necessary for that. So I have the overview, I have everything set up, and I'm going to do all the proofs. I'm going to continue this in part 2 of this video. Part 2 is going to come very soon. I'll have it up in a couple of days, and that is going to contain all the proofs of what I have outlined here. I don't want the video to be too long and too complicated to produce. It's better to break it up into 2 pieces. So all the proofs are coming in part 2, which is soon. And if you like this so far, I think this was a kind of a qualitative, intuitive discussion of what's going on. We laid all the groundwork. We understand the concepts. What is even partial sum, odd partial sum. We see the behavior of partial sums, this amazing behavior that goes like this, like this, like this, kind of reminiscent of continued fractions, you know. It's very interesting to speculate what's the connection there. This kind of amazing up and down behavior of alternating series and their partial sums. We've got all that. We have a picture in our mind. It's very clear now. So then the proofs will be a piece of cake. It will be really easy. The hard part is this video, is understanding all these concepts, and then the proofs are very straightforward. So I will see you next time.